Hello again, class. It looks like uh, the voiceover for my last presentation did not record after the 8-minute time, so I apologize for that. So I'm re-recording this. We're gonna catch up with locations and distributions. So we are still in the topic for z-scores and hypothesis testing. So going back to z-scores, in the previous 7 slides, we talk about z-scores being transforming the original scores into scores with a mean of 0 and standard deviation. I have emphasized this in the previous recording that in z-score, the mean is always the 0 and the standard deviation is always starts at 1. So for example, if you have different row IQ score, but you have a given population mean of 100 and a standard deviation of 15. So to convert the z-score for an individual IQ of 100, well, you just have to subtract what is the mean of the sample minus the population mean divided by the standard deviation, and that is 15. So for this case, the z-score is 0. What about the second one? What is the z-score for an individual with an IQ of 115? Well, you subtract again what is the mean of the sample and then subtract that with the population, with the known population mean, which is 100, and so that's 15. And with the standard deviation of 15, then you do 15 divided by 15 equals 1. So the z-score for an individual with an IQ of 115 is 1. The last example here is what is the z score for an individual with an IQ of 70? Well, 70 is the score, an individual score, minus the population mean of 100. That's minus 30 divided by 15, which is the standard deviation, and the answer is minus 2. So when we talk about that, the next graph clearly shows you what's the relationship of z-scores and its location in a normally distributed curve. Well, remember we have to go back to 0 because z-score 0 means that is the mean. And in this particular example, our mean was 100, so we have to put the 0 um, immediately below, below the 100, which is the mean score of the population. So anything above 0 is signified by a plus sign, and anything below 0 is signified by a negative sign. So an individual who scored 115 has a z-score of positive 1. An individual who scored 130 IQ will have a positive 2 z-score. And in the opposite, you have a minus 1 for those who scored below 100, which is the mean, and that would be minus 1 for 85, and minus 2 for 70, and minus 3 for 55. So why do we use z-scores? Well, it's a lot easier to compare scores from normal distribution using the different scale if we use the z-scores. Supposing you have two tests. Test A, Fred scores 78, but the mean score for this particular test is 70 with a standard deviation of 8. On another test, Fred scores 78 again, but the mean score this time is lesser. It's only 66 with a standard deviation of 6. Which of the two tests you think Fred did better? Well, if we apply z-score distribution, the concept of z-score distribution, it's very easy to solve the problem. For test A, the z-score is simply z is equal to what is the individual score, that is 78. You subtract that with the mean of the population, that's a given, so that's 8, and then you have the standard deviation of 8, so that's 8 divided by 8 equals 1. What about test B? Well, to get the z-score for test B for Fred, then you just simply put again what is the score of the individual, and that is 78 for Fred for the second test, and then the mean this time is 66, so that is 78 minus 66 is 12, and the standard deviation this time is 6, so 12 divided by 6 is equal to 2. Since we know that the higher the positive number from the zero, which is the mean in z-score, we know that Fred is doing much better on test B. In a distribution of IQ score with a mean of 100 and a sigma of 15, what would be the z-score for someone who score 130? Well, you can easily transform that. So you just say 130 minus 100, that would be 30, and then divided by the sigma, which is 15, and that will give you 30 divided by 15 equals a z-score equals 2. How do we interpret? Very easily. The z value indicates that the score is located above the mean because it's a positive sign by a distance of 2 standard deviations. So here's the formula. I think this is the most simple formula you ever have to remember in inferential statistics. The z-score is just the individual value or score that's represented by an x minus the mean of the population. It's a known mean of the population. You have to remember in a normally distributed in a normal distribution, you have to know the mean and the standard deviation in order to standardize them. So that's why it's a given. Mu and the sigma is always given when you talk about a z-score. And because of that, you can always create and locate um, where is the score of the individual in the entire distribution. So the numerator is the difference between a score and a mean, and the denominator is the standard deviation, and that is a very, very simplistic formula. So in summary, z-scores provide you a way of comparing scores on different row score scales. It gives you a given score, and it gives you an idea on how a score stands in relation to the overall sets of scores. It determines how well a specific score represents its population. And then a score of 0 indicates that the score is close to the population mean. Anything that's beyond +2 or -2 indicates that these scores are extremes. And then again, it gives you an idea. It makes the comparison from one individual score to the next individual score very easy to do. Moving on to probability. Probability is a very important concept in research. When you begin doing research, you always have a question about an entire population, and then an actual research is conducted only using a sample. It's too expensive to study the entire population. And then we use inferential statistics using the sample data that we obtain basically in order to answer the questions about the population. Now, the definition of probability is quite simple. It's just the probability of A means the number of outcomes that we classified as an A total divided by the total number of possible outcomes. For example, if you're selecting a card from a complete deck, there are 52 possible outcomes. And we know that the possibility of selecting of A's is 4 because there are four aces, or 4 cases of A's in the deck. And so you just simply divide 4 divided by 52 and you get 0.07, and that is your probability of selecting an ace in a card from a complete deck. What about the possibility of obtaining heads for a coin toss? Well, there's just two sides of the coins, the head and the tail. And so you can just have 1 divided by 2 or zero point 0.5 or 50% chance. So the probability of a specific outcome is expressed with a small p and can be expressed either decimal or percentages. When it comes to frequency distributions in relation to probability, well, probability usually involves populations of scores that can be displayed in a frequency distribution graph. I'll show you in the next slide. Different portions of the graph represent portions of the populations. And always remember that proportions and probabilities are equivalent because these are chances, but it has an exact amount of limit. And so when we talk about proportions, you have a certain amount and you're asking a small slice of that amount and you're asking what would be the proportion based on what would be the proportion of the small slice of a pie based on the total pie. So let me show that to you in a couple of slides that demonstrate really very easily. But before I do that, let me talk to you about random sample. Random sample simply means that the individual in the population has an equal chance of being selected. It is very different when it comes to a different concept when it is called random assignment. Random assignment is when there's equal chance to be selected within the specific parameters or features that the study would like to control in order to avoid bias in either one arm or the other arm, the control arm versus the experimental arm. I'll give you an example for random assignment. So all patients still have equal chance to be selected either getting the new drug or not the new drug. But if we know that if we know that deletion of chromosome 13 or deletion of chromosome 17 are really a negative prognostic factor for survival. So what you're going to do is you're going to do a random assignment. You cannot allow that all of the patients receiving the treatment will not have chromosome deletion 17 because we already know that that's associated with early mortality. So you want to do a random assignment. Each individual still has equal chance to be selected, but now you're trying to balance the characteristics, the feature of the two-arm control versus experimental using a very specific feature or characteristic of the disease to make sure that there's no bias. Probabilities must stay constant from one selection to the next if more than one individual is selected. Here, just follow me. If we use a very simple population that contains only 10 respondents or 10 scores, you have 10 with values of 1, 1, 2, 3, 3, 4, 4, 4, 5, 6. So you have 2 ones, 1, 2, 2 threes, 3 fours, 1, 5, and 1, 6. Those are your values. You create a frequency distribution histogram. So there you go, 1, 2, 3, 4, 5, 6, 7, 8 in your x-axis. And then you create your frequency. You put 2 blocks for 1 because there are 2 individual who had a score of 1, and then there's only 1 for an individual who scored for 2, and then there's 2 for an individual who scored for 3, and then 3 for those who scored 4, and then 1 scored 5, and 1 scored 6. So if your question is, what is the probability on obtaining an individual with a score greater than 4? In probability notation, you just simply put P times the probability of, and X is the probability of an individual scoring greater than 4. Well, simply put, if you go back, how many individual had higher than 4? Well, basically, there's only 2. One individual got 5, another individual got 6. So there's only 2 individual with a score greater than 4, and then you divide that by the total possible outcome, and that's 10, and therefore your answer is zero point 0.2 or 20% probability that we will obtain an individual with a score greater than 4. What about the last question here? What is the probability of selecting an individual with a score less than 5? Well, if we go back again to our frequency distribution histogram, our people who have scored less than 5 are all of these people before 5. So those who scored 1, 2, 3, and 4. So these are 5, 6, 7, 8. There are 8 individuals who scored less than 5. So that simply means that that's your probability of a given A, and then divided by the total outcome, the total possibility of an outcome, which is your 10, because we have a total n of 10. So basically, there's about 80% probability that we will select an individual with a score less than 5 based on our data. So normal distribution is a common shape. It's symmetrical. It generally use the mean and the standard deviation. definitely remember your measures of central tendency and measures of central dispersion when you talk about normal distribution. The highest frequency is in the middle, and a normally distributed um, data is definitely symmetrical to the mean. It is central to many aspects of inferential statistics because it can be used to answer questions concerning the probability of events. Can be described by the proportion of the area contained in its section, especially when you start talking about critical values. Like for z-scores, critical values would be anything above 1.96, that's plus 1.96, and anything below minus 1.96, those are the critical values. And we know that if your test results will fall within those critical values in the z-scores, that means that you have to reject the null hypothesis because your finding is definitely significantly, or what we call noticeably, different from the population mean. So here's the normal distribution appearance. Your mu is in the middle. Mu is the mean, and then your sigma is your dispersion. And again, that is a perfect normally distributed curve. It appears like a bell church. So that's why we call it the bell curve. And what we know that when we standardize the scores, just like when we use the z-scores already, that's your standardized distribution. We know that from 0 to plus 1 z-score, that accounts for about 34.13% of your sample. And then from 1 plus 1 to plus 2, that accounts about 13.59% of the sample. And then plus 2 or higher is about 2.28%. And so typically the outlier of your studies are the plus 2 uh, or higher, or the minus 2 or lower. So again, we are going to beat the horse here. If the IQ is normally distributed and we have a population known mean of 100, standard deviation of 15, in this particular normal distribution with z-scores, we can safely say that 68% of the people have IQs between 85 and 115, and 95% of the people will have IQs between 70 and 130, and about 99.7% have IQs between 55 and 145. So the normal curve and probability. The meaning of the distribution is that in z-score, the mean is always 0 and that the standard deviation is always 1. So what we know is that the mean of the distribution is 100 and that the standard deviation is 15. When you are given with this information, so this is again in a normally distributed data, we the population mean and the standard deviation is always given. So here our population mean, the given is 100 and the standard deviation is 15. So what the question is, what is the probability that a randomly selected student from this population would have an IQ score of 115 or greater? Calculate the z-score. Well, the answer is approximately 16, or 16% of the total area under the curve in the distribution. Moving on to the characteristics of the normal distributions. Obviously, in a normally distributed curve, the sections on the left side of the distribution have the same area as the corresponding sections on the right. So we should not have skewed to the right or skewed to the left. That is not a feature of a normally distributed data. Because the z-scores define the sections, then the proportion on area applied to any normal distribution is very specific and it has meaning regardless of the mean and regardless of the standard deviations. Because remember, this is now a standardized distribution. You can also use the unit normal table, but nobody does now that we have computers. I mean, we used to just look at, okay, the z-score, and then what is the degree of freedom, how many are there in the sample, and then you can look at the value, and then you can say whether it is statistically significant or not based on your level of significance. But now, I mean, computer does that for you. So probabilities, proportions, z-scores, these are all key concepts that are so important in inferential statistics. They actually are so interrelated to each other, and that you need to really understand probabilities, proportions, z-scores all together. You can't separate them. And the concept that if you already know the z-scores, you can definitely look up the corresponding proportion, and you can also definitely make an interpretation where that individual is in terms of standing um, when compared to other the rest of the sample. If you also know the proportion, you can use the table to find the specific z-score locations, such as using your table. Nobody does that anymore. And again, probability is equivalent to proportions. I think this is pretty self-explanatory. Probability and proportions are equivalent. Probability are chances, proportions are just a fraction of the total event, and same thing as probabilities. What's the chance? What is the probability? It's the possibility of an outcome for an A divided by the total possible outcomes. So they are exactly equivalent. How about probability and samples? Well, probability and samples. When we look ahead for inferential statistics, many research questions begin with a population that forms a normal distribution, just like what we talk about in IQ. A random sample is selected and receives a treatment to evaluate the treatment, and then we try to assess what is the treatment effect and whether it's statistically significant. Probability is used to decide whether the treatment the random sample receives produces an outcome that is noticeably different, or what we call statistically different, from the population. The key here is to define what is noticeably different, and that comes your uh, critical values. So the location of a value in a sample in a population can be represented with a z-score. The z-score tells us how noticeably different the value is. Remember that 2 plus in general in the z-score is definitely already towards the outlier section. The researchers will then aim to study many different samples rather than just one single values. And the sample provides an estimate of the population, and how many sample means and the many sample means provide an estimate of the population mean. Now, important concept when you do research is, of course, sampling error. This is a natural discrepancy or the amount of error between a sample statistics and its corresponding population parameters. That's because samples are variables. No two samples are identical. And so you sometimes could have a sampling error because your sample statistics and your corresponding population parameters, there is a natural discrepancy. Another important thing we need to remember is that samples differ from each other. The sample means differ from each other, and that the distribution of the sample mean is the collection of sample means for all the possible random samples of a particular size. That's your small n, that's your sample size, that can be obtained from a population. That's your capital N for population. What it tells you is that it provides a method for organizing all of the different sample means into a single picture. So here's a typical distribution of a sample mean. And again, you always put your mu in the middle, in the center. And this is your normally distributed um, data. And distribution can be the distribution of sample scores with only one mean. But sometimes distribution can be of many sample means. This is called sampling distribution, which simply means that a distribution of statistics obtained by selecting all the possible samples specific size from a population. The sample means pile up around the population mean, in the distribution of sample means is approximately normal in shape. That is the characteristic of the distribution of sample means. So here's an illustration of what sample means is all about. So everything piles up in the mean, in the middle. And again, there is a simplicity in this diagram because it shows you that everything, the distribution of sample means is approximately normal in shape, and the sample means pile up around the population mean. So this is what this graph is all about. When you also talk about when you talk about standardized distribution, it is definitely governed by central limit theorem. This is a theory that explains why many distributions tend to be close to the normal distribution because there's only a limit to there's always a parameters involved when you study, and that there is a limit, and they are pretty much centrally located, and that is why many of distribution tend to be close to the normal distribution. This concept applies to any population with a mean and a standard deviation, just like IQ, just like your entrance exam, just like income of a city or a town. So the distribution of sample means drawn from the population approaches the normal curve as the sample increases. So this is so true. When you have more and more subjects in your study, if you can get all the 3,000 uh, individual to participate in your study in a town that has a population of 3,500, you know very well that the distribution of sample means will approach a normal curve as soon as your population, your sample size increases. The other thing that we would like to always remember is the standard error. This is now based on the measures of central dispersion. So the standard error is the standard deviation of the distribution of the sample means for sample size, for the sample size, or your represented by your small n. There are two conditions in order for the distribution of sample means to be almost perfectly normal. Number one, the population from which the samples are selected is a normally distributed population. And number two, the number of scores in each sample is relatively large, around 30 or more. So that's why in a research there is this almost universal rule that you have to have 30 or more in your study when you do your t-test, because again you wanted to meet the assumption that the sample has the shape of a normal distribution curve. Magnitude of standard error, these are important concepts when we do power analysis. Let me walk you through here. The first one is the law of large numbers. This is a law that states the larger the sample size, the more probable that it is that the sample mean will be closer to the population mean. Well, this is very true, and that is why when in a large randomized controlled study, when you enroll 600 patients, what happens is that the sample mean gets closer to the population mean, and therefore the standard deviation becomes really, really small, or the variance becomes smaller, but you can still detect statistical significant effect of the treatment because of the larger sample. The second concept is population variance. The greater the variance in the population, the less probable that it is that the sample mean will be closer to the population mean. Well, if you have a small sample, you will have a big population variance. So what this means is that if your variance is actually very wide, you only need a small sample to detect that difference because you have such a great dispersion of the variability of your population mean versus your sample mean. Therefore, based on these two important concepts of law of large numbers and population variance, when we design study, we need to always have sample size calculation. That's what we call power analysis. We power our study at least by 80%. That means that it has 80% chance that it will detect the effect of your intervention. And then we also need to know the variance, because if we don't know the variance, then we will not know what would be the appropriate sample size that we need to prepare for our particular study. If we don't know the variance, then we will not know whether we need more or we need less sample for our study, because remember, the larger the variance, the smaller is the sample that we need, because we can easily detect the difference between the sample mean and the population mean. Whereas if the variance gets smaller and smaller, or if the variance is small, then you really need to have a large sample in order to detect the difference between the sample mean and the population mean. So I think that this is already very clear. If you have any questions, just make sure you follow up with me. But um, there is a software from Canada actually that's available online. If you're about to embark into a study, you can just email me, and just as long as you have the variance, the standard deviation, and what was the mean from previous study, and now you're about to start a new study, we can plug in all those numbers, and based on your research question, we will be able to have a power analysis with at least 80% power to detect the effect of your intervention to your variables of interest. So here's a distribution of sample means for samples of 1, 4, and 100. On the left side, it's very clear. You have a sample of 1. Look what happened to the variance. Very wide, 20. Sigma of 20. And what happens when you have 4? A sample of 4. Well, the the variance gets smaller. It's 10. So you have the mean is always in the middle. But now your sample mean is getting closer to your population mean. But when you have 100, look what happened to the variance. Standard deviation is 2, and then that tells you that the higher the number of the population, then the difference between the sample mean and the population mean gets very, very small. And therefore, um, in randomized controlled study, you can really detect the effect of the intervention, um, even if the um, even if the variance is too small, because they are so powered. They put 600, 700 patients in a study. Looking ahead, again, inferential statistics use sample data to draw general conclusions about the populations. We will also be able to tell differences between sample and populations that are introducing uncertainty into the inferential process, and it uses probabilities to draw inferences from sample data. So what is the logic of hypothesis testing? Well, we do hypothesis. We hypothesize all the time, every day. We come up with hypotheses in our day-to-day lives. But in strict sense, a hypothesis is a statistical method that uses sample data to evaluate a hypothesis about a population. These are the orders or the logic. We state a hypothesis. We predict the characteristic of the sample based on the hypothesis. We obtain a random sample from the population. Then we compare the obtained sample with the prediction made from the hypothesis. And if it's consistent, hypothesis is reasonable. If it's discrepant, then we know that the hypothesis needs to be rejected. So in a basic experiment, you have your treatment in the middle, and you have on the left side known population before the treatment with a sigma of 20 and a mu of 80. So for example, this is a cholesterol level. The mean cholesterol level is 80 with a standard deviation of 20. And then you introduce a treatment like a new drug. And let's find out what happens then to an unknown population after the treatment. What is the mu? What is the mean of this of this population after it receives the treatment? We know that the sigma is constant at 20, but the question now is what is the treatment effect of a new drug to lower the cholesterol? So the question is what would be the mu? What would be the mean of this unknown population after the treatment? And your hypothesis simply says that is the mean of the sample population noticeably different than the known population mean. So there are four steps of hypothesis testing. State the hypothesis, set the criterion, collect the data, make a decision. A null hypothesis simply says there's no effect or there's no relationship between the variables of interest. An alternative hypothesis states that there is an effect or a relationship between the variables. Step two, set the criterion for decision. You need to have your alpha level. In most research, the alpha level is always at 0.05, which has a confidence interval of 95%. The critical region is composed of the extreme sample values that are very unlikely if null hypothesis is true. So if your results is false within the critical region, then you know that it's statistically significant, then you're going to reject the null hypothesis. It's very unlikely that the null hypothesis is true, therefore you're going to reject it. So here is a very good illustration of an alpha level of 0.05. This is your normally distributed curve. So in the middle is your 95% confidence interval. There is a high probability that the values is going to fall within that 95% if the null hypothesis is true, assuming that the mean is 80, and that's the center of the bell curve. What happens then is that if your value from your sample belongs to the critical extreme value, which is to your right, it's the z-score of 1.96, and to your left is the minus 1.96 z-score, then you need to reject your hypothesis. It means that this is noticeably different or statistically different than the mean of your population. Any questions? This is so basic. I hope you really understand this because this is where you read a lot of paper that talks about alpha level of 0.05. And just remember the z-score for that is minus 1.96 to the left and plus 1.96 to the right. And again, remember the rule in a normal distribution that both sections are equal. And this is another concept about two-tailed t-test is that if you do not know the direction of your research, whether it's going to go positive or it's going to go negative, you always do a two-tailed test in order not to miss statistically significant results going on the opposite direction. The data collected after the hypothesis stated, those are in the step 3 now. Data collected after criteria for decision, also in the step 3, and then you compute your sample statistics, that is your z-score, to show the exact position of the sample, and then make the decision. Is it in the critical region or is it in the middle, in that 95% confidence interval? Hypothesis testing is an inferential process. It uses limited information, sample the data, and sample data used to draw conclusion about the population. Always remember, errors are possible when you do experiments. What are the errors? It's the type 1 error. It's when a researcher rejects a null hypothesis that is actually true. In other words, the researcher concludes that a treatment has an effect when it has none. When does this thing happen? Well, any violation in the integrity of the intervention can lead to a type 1 error. For example, there are synergistic events. You have a study and then you introduce your intervention, and then something during the time of your conduct of your research, something is being introduced, and that factor has a synergistic effect to your intervention, then that could be a type 1 error, because you actually, what happens is that a researcher concludes that a treatment has an effect when actually it has none. That's because there was a violation in the integrity of the intervention. So synergistic activity, um, uh, during the study, for example, if the participants have knowledge about certain aspect of the treatment and they start um, violating the integrity of the intervention, all of that, even the researcher. For example, if you're in randomized controlled trial and then you actually know which arm the patient is has been randomized, and then you may create some manipulation of the intervention, and again you will show then that there is a treatment effect, but actually it has none. So those are called type 1 errors. When we say the alpha level is at zero point zero 0.05, what we mean is that there's only 5% chance that the result is a type 1 error, which means very unlikely, if treatment has no effect, that the null hypothesis is true. So this is the only error that we are willing to take, is the 5% chance. But we need to watch out for type 1 errors, and type 1 errors is typically associated with the violation of the integrity of the intervention. What about type 2 errors? Well, type 2 errors is what happens when a researcher fails to reject a null hypothesis that's really false. So what happens here is that the researcher has failed to detect a real treatment effect. Well, this can be easily demonstrated by a small sample size. For example, if you did not determine the population mean and the sigma to get the variance, and you didn't do power analysis. And in a study, if you would have required 80 subjects for you to detect the effect of your intervention, but then you didn't do a power analysis, then you didn't know. And what happens then is you only enrolled half of the subjects that's needed to really test your intervention. So what happens that you're going to get a not statistically significant result. And so what happens then is that the researchers fails to reject the null hypothesis that is really false, because you actually underpowered, and then you think that the result is not critical. But if you would have really followed that you needed 70 subjects, then you will have probably the results that will fall within the critical region, and then you will actually reject the null hypothesis. So type 2 errors is the researcher has failed to detect a real treatment effect, and therefore it fails to reject the null hypothesis when actually it should have been rejected. But because of underpowering, small sample sizes, that is the source of type 2 errors. I'm gonna stop there, and I'm gonna stop there. I think, well, actually, I have a couple more slides, so I will not stop. So in the literature, when you read how are all of this being reported, well, a result is significant or statistically significant if it's very unlikely to occur when the null hypothesis is true. And we just put the p-value, whether it's less than 0.05. Sometimes you'll see a lot of 0.0001. That tells you that the chance is really, really very minimal. It's less than 5%. And they put the z-score, then you know that 3 plus is definitely an extreme value, because we know that z in a z-score distribution, 0 is the mean. And then as we see positive, +1, +2, +3, we know that those are already better than the population mean. And the higher the z-score, remember the positive 1.96 is the critical value of the z-score. We always state the significance. We report the test statistics, the value of test statistics, which is the z equals 3, and then we report the alpha level, which is our 0.05 alpha level. There are assumptions. I mentioned this earlier for hypothesis testing. It has to be random sampling, which means an individual has an equal chance. Has to be independent observations. And then number three, the value of standard deviations is unchanged. It has to be a given. There has to be already a standard deviation that you used uh, based on previous knowledge from previous similar studies, and that's how you calculate your sample size. And then there has to be normal sampling distribution. There's an assumption that the sample data will be normally distributed, because remember, we're using z-scores, and that is a standardized distribution. That summarized everything. And if you have any question, feel free to email me. I hope we have all the audio taken care of, and I can still see the microphone. It's still in green, so I'm hoping this should not pose any problem.